Hey, how y'all doing?
Good. How about yourself?
Doing okay. I was just in the kitchen. I got totally distracted. Like I thought, oh yeah, I've got plenty of time right before class starts up, and I was thinking about, okay, so I've got my yogurt here, but the yogurt's, when it gets all watery at the bottom, I hate that. So I was thinking about pouring it through one of those like coffee filters, so that way I could get the water out of it. And then I looked up and it said, "Oh, it's 10 after, time to start." And I thought, "Oh crap, I should put my yogurt back in the fridge and get to class." The nice thing about Zoom is like you can do that as opposed to having to run halfway across campus because you're a moron and late like me. Okay, so a couple things I want to just mention administratively, and then we'll get into administrative questions and other things. I was looking at the schedule for where we're at and where we're supposed to be at, and I know that we're going to be just fine to be ready for the second exam, which is, for better or worse, time for this week. Okay, so I apologize for that because it seems so darn quick. But really, the best thing to do is to have the content such that there's an exam right at the end of chapter five. So the test will be on chapters four and five, basically. And Probability concepts, and we're going to sort of cover basic probability today. And then tomorrow it will be discussion of random variables and sampling distributions. And sampling distributions is the heart of the statistics portion of the course. If you want to think about it this way, you know how you got the building blocks and you like build things up with Lego or whatever? Um, Sampling distributions, what's in chapter five, section five, which we should be talking about tomorrow, really gets after the question of how can we trust the mathematics behind the methods from here on out for the rest of the term. We already fit a trend line through data. Okay. The question that we'll be answering towards the end of the term is something more interesting. How do we know that the trend line we fit is reflecting a real characteristic in the population that we're sampling from and not just bad luck? Okay. So to get after that, we really need to sort of have chapter five, and in particular the later bits of chapter five, down solid. And so let's work towards the exam. I should have a sample exam online for you tomorrow, and then we'll talk about the sample exam on Thursday in class again. And so to get after when the test is, it will be released Thursday after class time, like probably about 1 o'clock on Thursday. But you'll have till Friday midnight to finish it. So you got, like, again, I'm adding in my head 11 plus 24, 35 hours to figure it out when you're going to take the test. And this is the same time frame, same time window as last time. Okay. It's just that it's different content. Okay. So I'm also noting when looking at class today, there's really only one challenging topic in the class today, in my opinion. Now, you're welcome to disagree with me, but the lab activity today is designed to sort of take you through the mathematics, but it's going to be more of a like do it on paper, or you could write it out, type it out with an equation. But you don't really need the equation editor for it. You can probably end up typing it into a Google Doc and you should be just fine. No data per se, but it is a probability exercise. It's called Bayes' rule. If you've bumped into it before, you're going to see it again today. Okay. So I guess one other thing, and that is about the exams. I've had questions from a couple of you about, okay, well, what about this or what about that? You're still entirely welcome to sort of let me know if you have questions about how exams were graded or what the right answer is, or how close your answer was to the right one, that sort of thing. Just send that to me in the form of an email. Maybe do a screenshot of what you wrote, plus then a screenshot of what I said the right answer is to the question. plus then indeed the question, and then sort of rephrase that in terms of, well, and why did I get the score that I got? I'm happy to explain sort of the grading algorithm, but the answers online I think are sufficient for most students to say, okay, yeah, I got it. I'm good to move forward. Okay. So do any of you have administrative questions related to this frickin' double-paced class and where we're at right now?
For the homework this week, 3A, what are the I don't know if this is meaningful at all, but the 5.3 and 5.4 sections are highlighted in purple instead of black text. Is
Oh, yeah,
that
yeah, yeah. I'm
significant at all?
sorry. I was trying to sort of indicate, yeah, will we get through that content? And I've made a determination, and that's based on what happened yesterday. But I neglected to make a change here. Only problems in chapters 5.1, 5.2, and 5.3 are due. The chapter 5.4 problems are going to correspond to tomorrow's class. And I'm glad you raised the question because I'll make that change after class. That literally anything in chapter 5, section 4, not for today, not due tomorrow. But it will be assigned tomorrow. It will be due on Monday, and it will be part of the content that is covered on the exam. So tackling those problems from chapter 5.4, 5.5, and 5.6 tomorrow, and asking questions about them on Thursday will be highly advisable. So I think I answered your question, Clara, but do you want to follow up at all?
No, that's good. Makes sense.
Okay. Anyone else for a clarifying question, administrative issue? Okay. How about any questions out of chapter 4 content? Chapter 3 and 4 content. Actually, just recent stuff. Something from yesterday. Okay, so what I'd like to do is to get into new content, and we're going to go through in class today a fairly formal presentation of set logic and basic probability. And this is something that in past classes in the last decade, what I find is students tend to say, okay, yeah, I've seen this before. Maybe in a high school AP stat class, maybe somewhere else. There's a variety of classes in the engineering curriculum where many students will have seen this previously. But even if you haven't seen it previously, it's something that most students feel pretty comfortable with. It's only when you try problems and therefore bump into like, oh, hold on, how do I put these rules together? That's the only thing where students sometimes say, okay, I would like to talk about this. And so the homework problems out of chapter 5.1, 5.2, and 5.3 that are being assigned today, those are the ones that I'm going to say, make sure you got it down, or you've got questions by tomorrow, because we'd love to answer clarifying questions to help you make sure you are comfortable with the content. And let me make sure I open up a chat window in case any of you type a thing, I would be able to see the thing. Okay, where's that? Right there. Okay. So as we go, I've noticed that you guys seem to be pretty good about putting stuff in chat. And if I don't see your question or your comment in the chat, definitely unmute and just let me know, hey, hold on, you overlooked me. Or, hey, I really had a question. Could you please clarify something along those lines? Okay. So I want to go into set logic to start with, and this is the style that our authors use. Okay. And to do that, I'm just going to say we're going to sort of use sort of a big old rectangle to correspond to what I'll call S, and that's like a script S. That is the sample space. And basically think, if I'm going to do an experiment, something could happen. The sample space is the list of all of the possible outcomes, okay? So yeah, literally, it's everything that could happen. So if it's roll a 20-sided die, I'd have the numbers 0, 1, 2, 3, 4, up through 19. Okay. And inside the sample space, we can list off various different possible events. And by an event, I'm just going to sort of like draw a little circle here. And you could think something like Venn diagram if you want to. I'm just going to say if something is inside A, yeah, what we have is that is part of the sample. That is part of the sample space in part of A. So A is just some set of possible outcomes. For example, A could correspond to a prime outcome if you rolled your 20-sided die. So like 1, 3, 5, 7, oh, primes are hard, 11, 13, 17, 19. Okay, so those could correspond to, something that could happen. The event B, okay, it's another set of possible outcomes. And I'm going to sort of, because I don't know what B is. I don't know whether B overlaps with A or not. In general, I might very well draw B here as corresponding to, well, maybe A is having some things that are in common with B. Maybe A has things that are not in common with B. Okay, so B could correspond to the result is even. Okay, so B could be even and A could be prime. And you're sort of thinking, well, I could list off all the possible numbers here, but I think in the intersection, prime numbers that are even, I've got exactly one outcome, 2. Okay. Again, the integers in the range 1 through 20, only 2 is both prime and even. Okay. So if I wanted to try to describe the sort of things that are sort of in both A and B, I might shade in that region. And I would write that the following way, A and B. Now, there's a lot of ways of writing that, okay? This is sort of the set notation intersection. It looks like a upside down capital U, but a little bit bigger. That's going to correspond to is in both A and in B. Okay? So any questions about that so far? Okay, so let's move forward and talk about, well, what if A and B are disjoint? Okay, so maybe go back to black here for my sample space here. If A, okay, is over here, A, and B is over here, okay, and there are no common elements, A and B are disjoint, A-R-E, disjoint. And I would write that A and B, the intersection of them, maybe I just write A and B, okay? If you prefer the word and to the intersection symbol, I would say that is a disjoint, or that's the empty set. So I'm just going to write a big old 0 with a big old slash through it. And someone always says that's like a weird capital 0. Someone says it's like a phi. I'll just call that the empty set, okay? So another term that you might want to be aware of is complement, okay? So if I've got an event A here, and that's sort of everything that's inside of that set A, the event A prime is equal to A complement. Not complement, but complement, okay? Or if you will, not A. Anything that is not in A is in A complement. And if I was shading that in, maybe yellow is a good color for shading, I'm going to sort of try and indicate like, everything outside of A is part of A complement. So if A were the primes, okay, A complement would correspond to like 0, 4, 6, 8, 10, 9, 10, 12, 14, 15, 16, 18. Yeah, okay, so that would be A complement, okay? everything that's not inside of A. Any questions on your friend A complement, or your friend the empty set to correspond to disjoint events? Okay, let me save this guy and clear it and then move forward. So, okay, what about a situation where we want to talk about not the intersection, but the union? Okay, again, A, B over here, A union B, or if you will, A or B. Okay. That could be written as, well, I'm going to shade in everything that's in A or in B or in both. Okay, so A union B basically says if you're in A, you're in A union B. If you're in B, you're in A union B. Okay, and I'm going to write that out a little bit carefully. I'm going to write A union B, okay, is equal to A union B, curly brace, it's A and B prime. Okay, so let's show that guy in hot pink. A, and also in everything that's not in B. So in A, but it's also not inside of B. Okay, so A union B is A intersect B prime. Okay, but I'm going to union that with, okay, A and B, things that are in both A and B. And let's pick a different color here. Let's go with the green color. Okay, that's the green there. And I'm going to union that with not A, but certainly in B. Okay, and I chose my words sort of carefully here to correspond to the and. Okay, and but not. Okay, you could say but in some cases. Okay, so the three highlighted things, the pink thing, the green thing, and the blue thing are the parts of A that are, white is not really a very good color here, the parts of A that are not in B, the parts of A that are in B, and then the parts of B that are not in A. I could take my union and chunk it out or break it out into these three separate chunks, these three separate bits. Any question about this rule? Okay. Moving forward just a little bit more. And now we're moving into probability. And we need to define the word probability. So let's do a quick diversion into probability. And maybe what I want to do is to highlight something that I had shown you here in the class video or in the class section. If you want to know more about the history of probability, this YouTube recording here is really very fun. Okay, and it's this guy Keith Devlin, who's a mathematician at Stanford, talking about these two guys who were trying to tackle a question. Okay, and the question was something like this: if you've got these people gambling, these two people gambling, and they're going to do a best 3 out of 5. So in other words, they're playing like backgammon. And individual A, if they win 3 of the 5 games, they take the entire pot of money. Okay, but if person B wins 3 games, they get the entire pot of money. Okay, so no problem, best 3 out of 5. We're pretty comfortable with that. But the situation gets complicated because what if they're able to play exactly 3 games, but person A wins the first game, person B wins the second game, and person A wins the third game. And then for whatever reason, they can't play any more of the games at all. They literally have to sort of run away. Okay, so someone's coming through town with a sword. This is like back in the day when people had swords and did this sort of thing. How should they fairly divide the money? You'd think person A has won two of the 5 games. Person B won only one of the 5 games. Person A seems more likely to win the next game or one of the next 2 games anyway than person B. So how can they fairly divide the money? And so these two mathematicians wrote back and forth letters for, I would say, about a decade. And between the two of them, they were able to figure out all the basics of probability theory that we know and love today. Okay. Another sort of a fun, sort of a quick read is the Paradox of Cheval de Marais. He's a gambler, and he sort of posed a question about 2 events that he thought would be equally likely, and it turns out that no, they're not even close to equally likely in terms of chance of occurring. And just watching the video or doing a quick read allows you some insight into games of chance and why and how probability works. Okay, so let's move into our definition of probability itself. Okay, so let's define probability. And there's really I'll say 3 approaches to probability, and not all of them are perfect. One of them is the classical approach. And the classical approach to probability follows all the same rules as we're going to talk about. The only weakness with the classical approach to probability is these classical people were back in the day, they're saying, we think at some basic level, everything should have a chance which is equal. Okay, so like if I roll a fair die, the chance of a 1 is equal to the chance of a 3, equal to the chance of a 4, equal to the chance of a 6. Okay, if it's a 20-sided die, each of those 20 possible outcomes should have the exact same chance, 0.05 or 5%. The classical approach to probability works great if you're willing to make an assumption. And the assumption about, what of these basic events are equally likely. And that's not a hard thing to do in some cases. Like if I were to flip a coin, here I got one right here. Sacagawea dollar. If I were to flip this coin right now, there's a 50% chance of heads. And so if I want to assume that and then move forward and say, well, what's the chance of getting 3 heads sometime in the next 8 flips? We could, by assuming classically that heads is equally likely to tails, and I've got n trials, we could find the binomial chance from that classical approach. Okay, so the classical approach, one reasonable thing to do. Our book doesn't take that approach, but a lot of people do, and they're not unreasonable. Second is a subjective probability. And to someone who has the subjective probability approach or mindset about probability, well, a chance means what they think it means. And so if this was a live class, I would probably ask you something like, what's the chance that the Raiders win the Super Bowl next year? And, after you're done laughing, some of you would give me a number like, 2%. Others would give me a number like, 8% because you're super optimistic. I'm a Raiders fan, but I'm not that optimistic. So can different people have different subjective beliefs about the occurrence of some event that appears to be unpredictable or uncertain in the future? Sure. Someone who has a subjective viewpoint might, however, disagree with someone else's subjective viewpoint. There's always someone in the class who's like a Dodgers fan and someone else in the class who's like a San Francisco Giants fan. And if you ask them, what's the chance the Giants win the NL West versus what's the chance the Dodgers win the NL West, it turns out that the two of them can't agree on numbers that match the rules of probability and also allow them to agree with each other. So subjective is fine, but you realize that's people's opinion. Okay, so here are the problems. We're not always willing to just make assumptions, okay? And you're not willing to go with someone else's assumptions, okay? So we need to go with something which is defined in such a way that we all agree on probability. And so we're going to go with the relative frequency definition. Okay, so the relative frequency definition of probability is just what our book and most people these days use. There's nothing wrong with either of the above approaches. Okay. In fact, there's a lot of really cool mathematics that people do with subjective probability that you can't do as easily with relative frequency approach to the definition of the word chance. The benefit of the relative frequency definition is there is one definition, and it has a downside to it, but at least we all agree on the definition. And this is the definition that most books are going to be using. And for a first intro textbook, okay, to any probability and statistics, if it does go with a subjective definition, there's nothing wrong with it. It's just it would be very unusual as something that engineers would be using as a text. Okay, so we're going to go with this relative frequency definition. And I'll say the chance of an event A, and I want to go with maybe curly braces, the chance that the random outcome A occurs, by definition, is equal to the number of times that A occurs over the number of trials. As the number of trials gets really very big. Let's just say gets bigger, gets to infinity. And in the long run, I might effectively, with this Sacagawea dollar, I might effectively never know the chance of getting a heads with this coin. That's the downside of this definition. I'll never know the chance of a heads with this coin because I could flip the coin and let's just, okay, I got a, tails. Okay, so 0 heads in 1 flip, tails, 0 heads in the 2 flips, heads, 1 head in the 3 flips. So that's like a ratio of 1 and 3. And you're saying to yourself, well, you've done this 3 times, but you got to do it more. And the answer is, yeah, I do. Okay, so let's go for 4. Okay, so easy, I can do this. Okay, another tail. So 1 head in the 4 flips. And you're saying, well, you got to do it again. And again, and again. Even if I'd done this 10 times, and some of you are thinking, don't do it 10 times, that's dull. Even if you do it 10 times, you will still never have hit infinite number of times of flipping the coin. You will never know the chance of heads on this coin. That's a downside, isn't it? Yeah, it really is. On the other hand, the other approaches are just, hey, what do you think? Or let's just assume heads and tails are equally likely. And those both have downsides as well. And the benefit of our relative frequency definition of probability is that even though you'll never know the chance of heads, at least 2 people with the exact same problem, okay, and the same definition of probability have to get the exact same answer. Again, you might not know indeed the chance of heads, but if this is the way you're going to define the chance of heads, okay, you will end up using data the exact same way in chapter 6 and later. These other approaches, you might not hit the same conclusion as your buddy who has a different belief set than you do. Downside. Okay. So let's give you some probability rules, and these are rules that apply to all 3 definitions of the word probability, although we're going to only use the relative frequency definition. Probabilities are such that 0 is less than or equal to the probability of an event A is less than or equal to 1. Whatever event A is, the chances in the range 0 to 100%. And you can sort of see that because the number of times that A occurs over the number of trials is never negative. It could be 0 if I never get a heads, or maybe if I get heads every single time, we'll have the ratio being 1. Okay, so probabilities are always in the range 0 up to 1 inclusive. Second, the probability that something in the sample space occurs is exactly 1. Something's going to happen. If I flip a coin, something will happen. I guess the 3 possible options are heads, tails, and like it lands right on the edge. Okay. That's possibility. Any questions about our definition of the word probability and our 2 most basic of probability rules? Okay. So let's move on to another sort of a definitional approach. If we have disjoint events, if A and B are disjoint events, the probability of A or B occurring is the probability that A occurs plus the probability that B occurs. Literally, disjoint events give me the chance of the union is the sum of the chances. Well, that makes total sense. Okay, so let's think about it with an example. Let's roll a 6-sided die. The probability if A is odd and B is the result is a 4, the probability of an odd or a 4 is the probability that it's an odd number plus the probability that's a 4. In this case, it's 1/2 plus 1 in 6, and that ends up being 2/3. Okay. So you're thinking, okay, yeah, I can do that. Let's use this rule and our earlier approach to chunking out the A union B for non-disjoint events, however. Okay. What if I've got non-disjoint events? And come on. Okay, wait and clear. Okay, maybe I can move this to here where I can do the clearing more quickly. No, I have it. Darn it. Mm-hmm. Okay, I'll put it right there. Good. Okay, so what if I've got events A and B possibly overlapping? Here's my sample space. The probability, I guess, let's rewrite A or B. Maybe I'm going to go with the union notation. A union B is equal to A and B complement, or A and B, or A complement and B. Okay. And so if I recognize all 3 of these are disjoint of each other, I guess if you're in the A and B complement part, you're way over here on the left moon. Okay. If you're on the A complement and B, you're on the right moon. And if you're in the intersection, you're in that middle football shaped zone. Okay. So we could write the probability of A union B because I've got these 3 disjoint events as the probability of A and B prime plus the probability of A and B plus the probability of A prime and B. Okay, so our 1, 2, 3 separate probabilities could be added together to be the probability of our union. Now I want to do a little bit of math with this if you're okay. Okay, I'm going to write this first 2, pair of the first 2, a little bit differently. And let's think about it for a little bit. A and B not, A and not B, a union with A and B. These 2 taken together, that's the first left football shape, okay? Plus then, I'm sorry, the first left moon shape, plus the football. I'm going to say these 2 shaded bits taken together, I could write that as just A, yeah? That's just A. So I'm going to write that as the probability of A. Okay. Now let's take the same approach, and I'm going to go with blue here. And I'm going to take sort of the separate or the second two parts. And I know some of you are thinking, but you're double counting the middle bit. I'm going to take the second two parts and just say, well, what are those paired together, unioned up? What is that? Well, that's the part of B that's not in A, plus the part of B that's in A. Overall, this is just a B. So the second portion that is highlighted here in blue is just the probability of B. But you're thinking you just added together four things. You added together the parts of A that are not in B, the parts of A that are in B, the parts of B that are not in A, and you added in the parts of A that are also in B a second time. That is unfair. Maybe what we need to do is to subtract out the probability of A and B, that intersection, to get back to exactly one of them. Okay, we double counted the middling bit, the middle football shaped region. We included it twice. We have to subtract it out. Okay, so here's a general rule that I think is sort of a worth remembering. This is the general addition rule, or the general union rule. A or B, the chance of that occurring is the chance that A occurs, plus the chance that B occurs, minus the chance that A and B both occur. Indeed, we double counted that middling range. We need to subtract it out once to get down to an even number of occurrences of the middle range. Any questions about your little quick proof, your graphic proof? Okay, so one more probability rule that I sometimes term the 1 minus rule. Here's an event A. Well, A, I'm going to write it inside here, and not maybe I'll write out here A prime, and let's erase that A there. Okay, so inside my sample space, everything's in either A or not A, and not A is disjoint of A. And from the earlier approach that we have, you could say that the probability, the probability of our sample space, probability of S, is 1. But S is written as the two just disjoint things. That's equal to probability of A plus the probability of not A. Okay, so there are two separate parts of the sample space. There's everything that's in A and then the rest of it, and those sum to 1. So algebra allows me to say the probability that A doesn't occur is 1 minus the chance that A does occur. Okay, so that's from your sample space having a total area of 1 and being able to add disjoint events to get the sum of the whole. Yeah. Okay. So any question about the 1 minus rule? The chance that something doesn't happen is 1 minus the chance that it does. So I'm going to put this in red and then again in blue. And well, no, blue. Okay, let's do blue and red and blue, and then also let's go with green, and then one more color for fun. Let's go yellow. Did I highlight this enough? Yes, you did, Steve. Why would I highlight it so much? Here is the wisdom for your homework. Here's the wisdom for an exam. If you can't see how to directly solve for a probability, re-express it in terms of, well, could I find the chance that it doesn't happen? And if you find the chance that something doesn't happen really easily, you can find the chance that it does with this 1 minus rule. Okay, so the 1 minus rule is your friend. Use that rule to your advantage. Any questions about the general basic rules? Okay, so there's one last thing that we need to do, and that's not really a basic rule, but it's a secondary rule that's implied by the earlier ones, but we're going to jump right into it. And it's called conditional probability. It's what we see in chapter 5, section 3. And we already even dealt with that, and you're, as a group, relatively comfortable with this. So I'm going to sort of do a quick example, and the event A could correspond to, let's just say, you get an ace when you draw a card off the top of a well-shuffled deck. Okay, and the event B could correspond to the card is a black card. Okay, and so I might want to know, what is the chance that it's an ace given that you know the card is black? Okay. What we're really doing conceptually is saying our earlier sample space there, S, we're saying we know that B has occurred. It's almost as though our new sample space, S prime, is just the event B. B has for sure occurred. And there's, in this new sample space, only a chunk of it where A is going to occur as well. Okay? Mathematically, the rules that we've just laid down for you in the recent, last 8 minutes, allow us to get to the following statement. The chance of A given B occurring, okay, B has occurred. You could view it that way. B has occurred already, or it will for sure occur. That would be written as the chance that A and B both occur over the probability that B occurs. That is your definition. Okay? And so it's easy to do work with this. So suppose we've got A as corresponding, we roll a die and we get a 3 or more. B could correspond to the result is odd. Okay. And so I'm going to tell you, okay, so maybe that's a 1, a 3, or a 5. 3 or more is 3, 4, 5, or 6 on the one die. Okay. The probability of A given B could be written as, what's the chance that the die is a 3 or more if you know that it's an odd result. Okay. That would be written as, well, the intersection of A and B, so odd numbers that are 3 or more, that would be corresponding to just a 3 or a 5. So that's the probability of a 3 or a 5. Okay. Over then the chance that the result is from B, that's a 1, a 3, or a 5. So that's a probability of odd result. So that's a 2 in 6 over 3 in 6. The ultimate chance is 2/3. Not hard to do. Simple example. Okay. So let's just move towards tree diagrams and how tree diagrams can be used within the context of conditional probability to help clarify thinking. If you have things occurring in an order, okay, a natural order, something happens first and something happens second, you might be given information like, well, A occurs, or maybe A doesn't occur. So you could list on the tree the chance that A occurs, or on the other branch, the probability that A does not occur. Okay. Second branch, we could have B occurs or it doesn't. B occurs or it doesn't. A probability of B given A, and the probability that B prime given A, okay, could be the second branch chances. So on the lower branches, you list conditional probabilities. Here's the chance that B occurs given A prime has occurred, and the probability of B occurring, B not occurring given A does not occur either. That'd be B prime down here. Okay. So if I tell you these 1, 2, well, yeah, shoot, if I tell you the first, you know the second, yeah? Okay. So if I tell you this one item, okay, and then if I tell you maybe a second item, and I guess you get B prime given A for free. And if I tell you maybe a third item, I'm telling you everything you need to know to solve a question. Okay. You get everything you absolutely need to know to solve a question if I give you just these 1, 2, 3 probabilities. So let's maybe do an example. And I like to call this the UPS problem because UPS drivers are drug tested. Okay. So let's say there's two events. The event D corresponds to the UPS driver is using, and let's just for now say let's that 5% of UPS drivers have used in the week previous to their drug test. So I guess probability of D occurring is 0.05. And so you know the probability that they're not using is 0.95. And then they might also test positive or they'll test negative. And if they are using, let's suppose the chance that they test positive, I'll put that within quotes because it's only testing positive. If they're using, let's suppose that's 98% of the time. But shoot, what's the chance that you will test negative? Again, within quotes, because it's, you're not testing positive. But that's the test result, not the reality. 2% of people who are using will test negative. So third pair of things. What if the person is not using drugs? Maybe some will test positive incorrectly because it's just a cheap blood test. It's UPS. They're not going to do like everything perfect. If you're not using drugs, then the chance you would test positive incorrectly is only 1 in 100. What's the chance that you would test negative given that you are not using? Well, we would hope that'd be most of them, 99% of the time, that's the case. So what I want to do is to sort of work with my basic setup. And again, these 1, 2, 3 bits of information, and maybe those are the 3 I want to highlight. One of the first 2, one of the second 2, and one of the third 2, I can answer the interesting question that at least management has. If someone is actually testing positive, what's the chance that they're using? Okay. So I'm going to go ahead and do a little bit of erasing here and put some of these numbers. Well, I'm going to redo my tree diagram to correspond to this new situation. Okay. And let's erase these guys. And friends over here also get erased, and there, yay. Okay, so I'm going to go ahead and so work in red. There's the people that are using D, okay, and D prime. And then they might test, so the D's are down here, and then they test positive or they test negative. The probability that they test positive given that they're using, okay, so the probability that they test negative given that they're using, okay. Then of those that are non-using, some of them will test positive given they are not using, and some will test negative given that they are not using, D prime. And let's plug in those numbers now, and I'm going to go with this bluish color, 0.05, 0.95, 0.98, 0.02, 0.01, and 0.99. Maybe plus and a minus there, okay? So overall, I want to aim towards the chance that they're using if they test positive. And we know by definition, this is equal to the chance that they're using, let's go back. They are using and also test positive over the probability that they test positive. Okay. So we could find the chance that they're using and test positive by multiplying things out, okay, using our conditional probability rule. You could multiply the chance of them using times the chance that they test positive if they use, okay? So that's going to give me my numerator here, 0.05, 5% using times 98% chance of testing positive if you are using. And then in the denominator, it's just the chance that they overall test positive. And there's 2 ways of testing positive. Either you use and then you're testing positive over here, or you're not using and you test positive anyway. So our first term is repeated, 0.09 times 0.05 times 0.98 plus 0.95. 95% of people are non-using, but some of them will test positive falsely, and that's going to be 0.01 of the time. Okay. So I'm thinking at this point in time, it's a math question. You could plug and chug in here, but the ultimate result ends up being 0.0585 if I did my numbers correctly. And so let's think this through and say, what the hell? And let's figure out what the hell. Okay, so yeah, 5% of people are using. Yeah. 98% of the users we catch. And 99% of the people who aren't using, we spot as non-using. And so if someone is testing positive, how is it that there's a nearly 6% chance that we think they're using? We think 6% of them are using when only really 5% are. It's because we catch nearly all of the real users, nearly all, not all, but nearly all. But of the non-users, and there are a lot of them, some of them are falsely flagged as using incorrectly. And overall, the math here, Bayes' rule, which is the topic of your lab, walks you through these calculations. And I hope the exercises in the lab give you some practice with this and that you feel pretty confident moving forward. I'll just say, I'm happy. I want you to be happy. Let's just all be happy together and call it a day, because it's time to close off class, but you got the lab activity. You're working in the same groups as before, so that's a good thing. Let me stop the share. Any questions about anything before we call it a day? Okay, again, you're working in your lab groups, same ones as you were in yesterday. And if any of you request that we change up lab groups between week 3 and week 4, at the beginning next week, I'll sort of have you sign up yet again for lab groups. But most people are pretty happy at this stage. But, we'll make changes if that needs to be the case as we go. So let me know if there's an issue. But otherwise, same lab groups as yesterday, and we'll be doing it for the rest of the week as well. We'll see you in the future. Bye-bye.